now it's...
Okay, perfect.
Yeah, so now the recording has started, but I think we started, so now it's 15 past. I think we wait 1 minute to see if we get more people attending.
I will start to share my screen, so I can check if everything is okay meanwhile.
Yeah.
Can you see it?
Yeah, but we don't see it in full screen. Can you make it full screen?
Here?
Yeah, perfect.
Oops. Okay.
It looks good.
Okay.
Okay, so then I think we'll start. So good morning, everyone. I think it's morning for most of us, at least. And welcome to this session on decarbonization policies. So my name is Knut Rosendahl. I'm sitting here in my kitchen in Norway. Decarbonization policies is a very important topic, and it's also become even more hot topic now with a new report from the IAEA on net zero emissions in 2050. And we have 4 interesting presentations today, at least from the title and the abstract. We have 25 minutes for each presentation, or 20 minutes for the presentation, and then 5 minutes for questions and comments. And I will let you know when you have 2 minutes left of your presentation. If you have questions or comments, you can either raise your hand in Zoom, or you can write in the chat. But we will not take questions during the presentation. We take it after the presentation. Okay, then I think I'll just give the floor, the virtual floor, to the first speaker, Gaëlle Le Treut. So please, the floor is yours. And the title, as you see, is the multi-level economic impacts of deep decarbonization strategies for the energy system. So please go ahead.
Thank you very much, Knut. Hello, everyone. I'm Gaëlle Le Treut. I'm a researcher at CIRED in Paris, in France, but now I'm sitting in Bordeaux, in more south west of France. So I'm glad to be here and to present my work at this conference. I would like to thank the IAEE organization committee to manage to make that event happen despite the circumstances. So I'm going to present a work entitled the multi-level economic impacts of the decarbonization strategy for the energy system. This is a work that has been done with my colleague Julien Lefèvre at CIRED, and also the collaboration of 2 colleagues from the Fundación Bariloche in Argentina, where I spent a few years as a postdoc there. This is a work also that's under revision in the Energy Policy Journal so far. So the presentation will follow standard outlines. I would say a few words on the context of this work and the research objective. Then I will provide an overview of the methodology. I will show you key results, and I will move to the conclusions and discussions. So at this stage, almost all countries are urged to change the scale of their commitments and must seek for drastic emission reductions by developing explicit deep decarbonization strategy. I will call it DG in the rest of the presentation most of the time, with short-term actions to reach the long-term target, which is net zero emission. So this is really the entry point of our work, which have taken part from the DDP project in Latin American Caribbean from IDRI, coordinated by IDRI in Paris. So designing deep decarbonization strategy should rely on 2 milestones. The first is that their development must be tailored to the national context to take into account the domestic specificities and the structure, of course, of the emission. Where are the emissions? What are the potential of mitigation? It's really specific to the national context. And a second one is that the decarbonization pathway must be built on feasible technical solutions and feasible pathway that details the sequences of the transformation. So most of the time, the decarbonization strategy devotes particular attention to the energy system to reduce energy-related emission, which are in fact the emission under scope of this paper. I would like to stress that we have made another work that includes all greenhouse gases emission, but here in this paper we focus only on the the emission from the energy system. So to be helpful, the strategy should provide quantitative information. So we start from qualitative information consistent with the national policy recommendation and the local context. So this work has been done by my colleagues in Argentina. And then we quantify, based on this qualitative information, key elements of the corresponding law pathway to be able to address some concerns around the transition. So the first thing is to be able to characterize the underlying deep transformation of the energy supplies and also the demand, and to be able to answer the following questions, which is how such transformation as a whole would have a wide range economic implication, not only in the energy industry, but also in the rest of the economy. So the final objective will be then to highlight the enabling conditions by identifying the loser and the winner of the intended strategy to better initiate the transition and avoid the block points. So to deal with such issues, we have developed an integrated approach based on loading full energy system pathway into a multi-sector economy-wide model. So we work on the Argentina, which is a good study case, we assume, because it gives a good illustration for the global challenge. So I jump now into the description of the approach follows. So as I said, we have first designed full energy pathway that reflects the view of various stakeholders in Argentina for a future decarbonized energy system. And we quantified this narrative, and to do so, the model LEAP has been used. So LEAP is an integrating energy planning and climate change mitigation assessment modeling tool. The model represents a detailed energy system at country scale, in our case Argentina, and to formulate energy plans consistent with the national context. So it makes it possible to develop full backcasting scenario that ensure consistency between strategic proposals and energy choices. So the LEAP Argentina model that my colleagues have been used have been already used in the past for mitigation studies in Fundación Bariloche, and it is used here to quantify the full decarbonization energy pathway, relying on feasible technical option for Argentina, which is quite new, such a study in Argentina. So the model provides us key information and paths of transformation for the intended DD strategy. So in particular, it provides the consolidated energy balance, capital expenditure, and operation and maintenance costs, but also investment expenditure of the particular power sector, which is key towards low carbon energy system, especially in Argentina. So for assessing the multi-level economic impacts of the decarbonized energy system, we used the IMACLIM country model, which is a multi-sector computable general equilibrium model available in several national versions. You will see another one version in this session. In fact, some of them are now hosted in an open access platform for the sake of transparency. So the model simulates a full picture of the economy under energy emission economic constraints, and it can assess without any couplings the macroeconomic cost and multi-sectoral impacts of an oriented policy, such as, for example, carbon price measure. So the model departs from standard CG approach by computing possible underemployment of production factor, which leads to unemployment. I would like to stress that the capital supply is treated as demand-driven, at least in the version used in this paper, through the proportionality link between capital consumption and investments. The description of the consumer and the producer trade-off have been made to facilitate a calibration on bottom-up expertise or a bottom-up model like LEAP. In fact, indeed, the model is hybrid for key sector, for energy sector, in fact, in this case, in the sense that it's calibrating on actual volume in ton oils of equivalent of energy, and also on monetary flow. So there is a dual accounting system here linked by a consistent system of price. And finally, one original feature of our modeling approach for this paper, which is specific to this paper, is that we capture the intersectoral links of the investment demand. So we implement what we call the investment matrix that describe which activity are driving the investment demand. So normally investment is like a vector in a CG model, and we open it into a matrix. As I said, we work on the case of Argentina. The IMACLIM Argentina model has been developed for the purpose of this paper. The model is calibrating at year 2012, and it represents 90 sectors. 6 of them are energy sector, which have been hybridized. So there is energy, ton oil equivalent. And then we have some quite standard compact disaggregation of the rest of the economy with certain sector. So finally, we link the LEAP and the IMACLIM model. So I will go into more detail in the next slides, but before that, I would like to stress that we have settled a one-way linking process, as we want to assess the economic impact of a predefined energy strategy, which is by definition not necessarily optimal. And we assume that the economic feedbacks do not affect the dynamics of the transformations. So LEAP first give information, as I said, on the energy balances. So we convert these energy balances into IMACLIM compatible format, which is an input-output table in volume. And thanks to that input-output table, we can assess energy intensity of production for the intermediate consumption that we will inform exogenously into IMACLIM. We will also inform exogenously the household consumption of energy and the energy trade also in volume, so for import and exports. So this comes from the energy balances at each time step of resolution. And then we made a particular effort to embark detailed information from LEAP into IMACLIM at each time step for the power sector, as it is key for achieving the low carbon transition. So LEAP provide time sequences of installed capacity per technology that we can cross with the corresponding capital expenditure and operational expenditure to assess the total annualized capital cost and fixed operation cost. And the growth rate of this cost is used to calibrate the increase of capital and labor costs in the power sector for IMACLIM. Hello?
Good. Oh, yeah. Okay.
Did you lose me a long time ago?
No, like only 1 minute.
Sorry, when?
Only 1 minute.
Okay, I will screen my screen. Sorry about that. I don't know what happened.
I also fell out. I'm not sure what happened.
Is it okay?
Yeah, it's fine.
Did you see that before? Well, I will start with the investment expenditure. I don't know if it's okay. Hope so. So I was saying that in the power sector, LEAP also provides a specific time profile per technology on investment costs. And by crossing this investment with a sectoral breakdown in terms of investment goods, we can assess the investment structure of the power generation for a given pathway. And this structure is assimilated into IMACLIM to the vector of the power sector in this investment matrix that we have described at calibration year, at base year. So let's move to the scenario that we have simulated. We simulate 3 energy scenarios. The INDC scenario is our reference case. It simulates the measure that have been already committed for 2030 by Argentina, and we extend it into 2050. There is a continuity on oil and gas, and there is not so much progress. It's not a very strong commitment here. And then we have 2 deep decarbonization scenarios that are based on common demand-side mitigation measures with strong efficiency gains, significant fuel switch, and electrification of uses. But they are on different vision of decarbonized power generation system. So on the one hand, the DDP exploits the Vaca Muerta basin, which is a huge hydrocarbon basin in Patagonia, to feed a growing power generation system, but it coupled it with the CCS technology to reach the low carbon emission targets. And on the other hand, we have the DG2 scenario, which rely on strong development of nuclear and also hydropower, but to a lesser extent. And the development of wind and solar are also similar in both DD1 and DD2. So moving to the results, I will not present the transformation of the energy system per se, but I will directly present the multi-level economic impacts, which is focused here. So first, our results show here the magnitude of investment required to decarbonize power generation in Argentina. So here I picture the mean annual investment and its mean share out of total investment over the period. It's between 2015 and 2050. So we can see that the share of investment used for power plants increase in both DDD scenario compared to the NDC scenario. with about 2 percentage points more. And we can see that the power generation costs are higher in DD scenario. Also, the higher cost of the nuclear compared to the cost of the gas coupled with CCS technology made that the DD2 scenario it's more expensive than the DD1. And here we also can see that the investment in wind and solar are the same in DD1 and DD2. And that in INDC we only rely on gas without any CCS technology. As macro insights, our results show that the DD scenario, have limited GDP implication, which are in yellow here. We show the net present value of cumulative GDP losses in DD scenario compared to INDC, but there are significant changes on the GDP composition from the demand side. So on the one hand, the share of investment is higher in both DD scenario compared to the INDC in orange, which are mainly driven by the massive investments, in fact, in the energy system, as we have saw it earlier, and also in low carbon equipment, in fact. Which has in fact a stimulus effect on the global economy. But on the other hand, there are also welfare implications, but they are limited, and competitiveness losses due to higher domestic prices. And the negative effects is higher in the DD2 scenario, which have higher electricity prices.
We got 2 minutes left.
Go quick. Here I picture the mean annual production compared to INDC and the unemployment to provide sectorial insight and not give only. We can show that despite lower energy supply in the DD scenario, I didn't show that picture, but it's hampered the production, but because it's more labor intensive, we have job creation in the energy sector, but this job creation has a lot of disparity within the energy sector because, of course, there are job description in the fossil fuel industry. And we show that upstream activity that provide low carbon activity have higher production level. We can see clearly in the construction here, which are much more mobilized in the DD2 scenario because of the construction of nuclear power plants, and in the DD2 scenario, it's more the rest of manufacturing industry that are mobilized for the technology goods. So there is a negative balance here of unemployment in our result, but it's small compared to the total employment. Sorry, I went quick, but I would like to go to the conclusion now. Obviously, we made some assumptions here, and I would like to stress some limits here. First, our modeling approach assumes perfect adaptation of the labor force, which means that there is no friction related to skill shifts and industrial restructuring of the economy. There is also optimal financing condition with no crowding out of low carbon investment on the other economy. And as a third structural assumption that we have made, I would like to state that we haven't implemented specific industrial strategy for the low carbon equipment supply. We assume, in fact, that the domestic market share for the supply of key low carbon equipment follow the average of the manufacturing industry in Argentina. Which are in fact calibrated at base year. So higher import market share of low carbon equipment will have negative implication on the results. So this being said, our work make it possible to give insights on the economic feasibility of deep decarbonization strategy for the energy system, at least here. We have shown that decarbonizing the energy system implies sizable structural change in the economy at time horizon and significant investment efforts. So there is a strong shift of the value added, not only in the energy sector, but also in the rest of the economy. And the upstream industry, the construction, for instance, will be provides the need of low carbon infrastructure are the winner of this transition. So to conclude, because I'm running late, more broadly, we are focused here in assessing the economic impact of a decarbonized energy system, but the paper also discuss the fact that the decarbonization strategy should also come with consistent global planning, which is why we wanted to focus on sectoral impact. Action plans like training program or labor mobility are important and must be anticipated, and well, complex policy package with financial dimension also should be discussed with stakeholders, together with consistent national strategy to mobilize the effort needed. So this is something that are often overlooked, and this is important to have clear enabling conditions to trigger really the decarbonization initiative. So sorry for to running late, and thank you for your attention, everyone.
Well, thank you very much for a very interesting presentation. So we have some time for questions or comments. So raise your hand, or if you can also write in the chat if you prefer. So let me just ask one question first. So if I understand correctly, you start with the energy model and then you take output from there into the CG model, but there is no feedback going back to the energy model. So there is no iterations, if I understand correctly. So is there a problem with that the results that there can be inconsistency in the results between the two models then, or?
Well, in fact, we made the exercise just to see it. It didn't change a lot, actually, and we would like. I quickly say it, but after we went to this exercise to make all the loops, but we have decided that we wanted to really show the impact of of an energy system that are prescribed. So in actual life, we decided we are building these plans, we will invest, and what would be the consequences of this predefined plan. So this is why we have decided to keep it that way.
Okay, I understand. I don't see any other hands, so let me ask one more question then. So you had in your CG model, you have unemployment, right? And if I understood correctly, your results had unemployment or more unemployment, but is that also the case in the long run? So it's not just a short run, but also a long run effect? Or? Yeah,
you mean if I keep describing unemployment on the long run?
Yeah, or in the results.
Yes.
Okay.
Yeah. Yes.
Yeah, one question. Yeah.
Just to quickly complete, we have an employment, we have a labor market, in fact, which are not entirely used, and in the deep decarbonization scenario, there is a quite small job destructions, as I said, but it's small compared to the out of the total of the jobs.
Yeah. Okay, Gauthier.
Yeah, thanks. So I had a question regarding, so you have the two DD scenario, and so basically in one scenario you do a variable renewable, so wind and PV, and then you complement that by gas with CCS, and the other one you do the same, but you complement it with nuclear. I was wondering in terms of flexibility of the energy of the electricity system, if you compare what was for example the need of battery or backup generator in the two scenario, because usually when as nuclear is capex intensive, you prefer to run it baseload, and you would like to actually limit its total capacity, so not building it for the peak, while normally gas plus CCS is less capex intensive, is more opex intensive, and so you rather optimal solution rather lead to maybe sizing up to the peak and then be more viable in its operation. Is it something that was considered in LEAP, or or maybe not assessed at this level?
LEAP, it's not my expertise area. It's my colleague from Argentina who run it, but I'm quite sure that yes, it's taking into account. It's all the energy systems that are built into LEAP are consistent in terms of base load and peak, and the peak of electricity and so on. So I guess
only data. It's at early level that you do the simulation.
Sorry, I couldn't hear you.
So normally with renewable integration to really go to, and probably it's not sufficient, but to assess, okay, what's the flexibility need? It's usually necessary to go to the early level to do the, to see what's the optimal mix. Normally it doesn't change much for IMACLIM and for large system impacts. And so I'm not saying that it's, yeah, to quantify somehow what are the flexibility needs in terms of batteries or in terms of presence of capacity at peak, it's usually required to go at least to early level to see a little bit what is required. And so I was wondering if you went up to that details or not.
I couldn't answer that. I had to ask to my colleague from who ran the LEAP model.
Okay, good.
Okay.
Thank you both. I think we need to move on also. So thanks again, Gaëlle, for an interesting presentation. So next one is Salaheddine Soummane. If you can share your presentation. The title is Structural Transformation of the Saudi Economy in the Context of Global Climate Action.
Can you see my screen?
Yes, can you make it full screen?
Yes, I will move to the full screen mode.
Yes.
Perfect.
Perfect. Yeah.
Thanks, Knut, for the kind introduction. And I'm very pleased to catch with some of you, especially Gaëlle. You will notice that the style of my presentation is quite similar to her presentation because we used to belong, I used to belong to CIRED while I was doing my PhD as Gaëlle. I was focusing on the Saudi case, which is the title of this presentation. The title changed a little bit, just to mention, it is now Structural Transformation Options of the Saudi Economy under constraint of depressed world oil prices. So the work was jointly conducted by Frederic Ghersi and Franck Lecocq from CIRED. And I completed it while at the lab before moving to KAPSARC, where I work currently. So the content of the presentation will be, as I mentioned, quite similar to Gaëlle's presentation. I will briefly, just to put the time to make sure I will not exceed the 20 minutes. The research questions, the context, the methodology, I will share with you the results that we run with the IMACLIM version of Saudi Arabia, and then I will provide some conclusions. So the research questions is, just to give you some background as well, we started as we move towards a more stringent climate policy. What could be the consequences for the largest oil economy or the largest oil exporter, which is Saudi Arabia? So we tried to assess this in our first paper, but then the question comes, we suggest that there will be losses for those oil-based economies of the Middle East. And we always talk about diversification, citing, for example, the example of Norway or the Emirates as a mitigation means or a mitigation tool to help these countries mitigate the impacts of climate policy and help them at the same time achieve their climate commitments. So the first question was assessed or answered partially in a different paper that was released 2 years ago, where we discussed the consequences of a low oil price scenario for the largest oil exporter, which is Saudi Arabia. And then comes the question of how to assess economic diversification, or what is simply economic diversification. So we try to have this contribution to those work streams, especially very relevant in the context of climate negotiations and very relevant to oil-based economies of the Middle East. So this paper is probably one of the first assessments of diversification policies and energy sector reforms as a mitigation tool, since it is based on a climate compatible oil price scenario beside a very recent paper that was released using a similar CGE framework for Kuwait. So the context is the following. Climate policy is now a very pressing issue, especially for the countries that are depending on fossil fuel. It is as old as the establishment of the UNFCCC in 1992, and it was explicitly mentioned. We can refer to the articles of this treaty. If I remember well, it's Article 14.8, if I'm not mistaken. And it was again mentioned throughout the recent IPCC report, where it is acknowledged that mitigation policies can reduce revenues for fossil fuel exporters. But there will be differences between regions and fuels, which make assessing these policies or the effect of these policies in a national context even more relevant. And this is what Gaëlle did previously for France and for Argentina, and what I did for Saudi Arabia. But we have several versions for India, South Africa, which are quite similar, but all in this work stream of having nationally compatible scenarios and modeling capabilities. And of course, when it comes to oil, we speak about OPEC. So OPEC is now pushing to acknowledge even more, and it is true that there is a unique situation of developing countries, including those that are dependent on oil, which must be taken into account if we want to reach a consensus in the climate change negotiations, which will ensure a fair transition to everyone. Why climate policy is a threat or a challenge for these economies? We can illustrate it simply by taking the scenarios of oil prices. I focus here on the oil price scenarios that are within the IAEA report, which is one of the most authoritative outlooks. And there are other outlooks that are existing, but if we look at a 2 degrees or 1.5 degrees scenario oil price that is compatible with this target, this oil price, since the demand is lower, the oil price will be structurally lower under these scenarios, which poses a threat or a challenge to economies that are to a large extent, such as Saudi Arabia, depending on oil revenues. So the work stream is the following. We have a lot of quantification of the consequences or the impacts of economic losses, mostly losses, for the Middle East oil exporters from climate policy. Our assessment is specific to Saudi Arabia, but there are other papers that assessed or quantified these losses on a regional basis. And all of the three papers, if I'm not mistaken, they all conclude that the Middle East region is the region to experience the highest losses in the case of a stringent climate policy implementation. And then we move to the second segment, which is mitigation actions. And the first one that we have in mind is diversification. Diversification is always presented as the only sustainable means to offset the economic losses from climate policy. And this was illustrated by the articles that I'm citing here, but those are all qualitative assessments. So we took the challenge to represent this in a quantitative framework adapted to Saudi Arabia. How we did this, description of the methodology again is quite similar to Gaëlle's framework. We have a hybrid economy energy computable general equilibrium model. We have 13 sectors with 4 energy and 9 non-energy sectors, which we spent a lot of time trying to hybridize the data. Hybridization is basically, as mentioned before, to have this representation of physical flows in tons of oil equivalent that are within the model as well. So we have the economy block, but we have the counterpart of the physical flows that we take into account as well. Here we don't rely on the leap, but in a similar framework or in a similar logic, we embark information from a specifically designed bottom-up model called the KAPSARC energy model, which has up to 6 energy sectors and detailed representation of the energy sector in the kingdom. The model compared to other or previous models for Saudi Arabia is not a static model, but is a dynamic recursive model. And we have annual steps up to 2030. And we are certainly looking to expand this up to 2040 or 2050. We have a representation of secondary income, which is very important from the household perspective, but also debt accumulation dynamics, which is very important from the government perspective. Our model, as mentioned previously, departs from the standard CGE model by having second best features, and we have 3 departures from the standard CGE. Market or the labor market here in the kingdom is quite rigid. We don't have a cleared employment or equilibrium employment, but rather we have a wage curve that results in having an equilibrium in employment. Another specific aspect is that we have administered energy prices, since it is the case here in the kingdom. Almost all energy prices or all energy prices, whether they are intersectoral or final energy prices, are administered by the government. And we have imperfect non-energy markets, which means that the capital is slightly distorted in terms of movement within the sectors. Those aspects, we add on top of them, accounting for some other specific features for the Saudi economy. We have the first one and the most obvious one, which is quite distorting for CGE framework, is the currency peg. In the kingdom, we have a currency peg that was lasting for over 30 years with a fixed nominal exchange rate against the US dollar. And this relationship or this rule induces some specific movements of the real effective exchange rate, which we discussed in our previous paper. The second one is that we have a savings buffer, which means that we might have some counter-cyclical macroeconomic policy by the government, which uses its savings to absorb the decline or shocks in oil prices. In terms of CGE modeling, this translates into what we call the Johansson closure. And finally, the energy prices, which are administered by the government, and the 4 sectors that we are having here, we have crude oil, natural gas, refined products, and electricity, whether they are intersectoral, for example, selling natural gas to the electricity, or final consumer prices, such as electricity for households use. Moving now to the 4th section, which is the simulations or the application of our IMACLIM Saudi Arabia model. We tried to simulate, or we simulated basically 2 scenarios. And these 2 scenarios are the scenarios that were presented in the national climate policy, in the nationally determined contribution submitted by the Saudi government before the Paris Agreement. We have 2 scenarios. The first one is what we call a continuity scenario, and is based on a continuous expansion of energy intensive industries. We have, in our model, we have petrochemicals, we have cement, and we have mining industry. Or we have the second scenario, which is a shift toward non-oil activities, and those are mainly services and manufacturing. We have tourism, financial intermediation, but also manufacturing industries. The first scenario is based, again, the challenge is how to deal with a 2 degrees or a 1.5. Here it's an older version, but it's a 2 degrees with efforts to beat 1.5 scenario, 1.5 degrees scenario, consistent oil price. Since we are targeting energy intensive industries, we don't assume any additional reforms of energy prices beyond the 2 waves of reforms that were implemented by the government recently in 2016 and 2018, which were quite significant. We don't have energy efficiency gains since energy will remain cheap, which means that we are not incentivized to have efficiency gains. And we have boosts of exports, and the growth is mainly driven by the expansion, as I mentioned, of the minerals, petrochemicals, and the cement. In contrast, we have the second scenario, which is the transformation scenario. Again, dealing with the same challenge of low oil price, but in this scenario, we have additional reforms of domestic energy prices and corporate tax to meet international levels. We recycle the additional revenue as investment in non-energy intensive sectors. We have energy efficiency gains, and we have exports driven boosts of the manufacturing and services sectors. The results are the following. To give you a broad macroeconomic snapshot of the economy in 2030 under these two scenarios, as you can see, I don't know if you can see the mouse moving. So as you can see, we succeed to have a higher activity under the transformation scenario by 1.3%. We have slightly lower trade balance since the economy or the export content of other sectors such as petrochemicals, mineral, and cement is slightly higher than the export content of the non-energy intensive sectors, but it's not a bad result since the trade balance is positive as well. But what is important is, and very relevant to the Saudi context, is that the unemployment rate is 1.7% lower under the transformation scenario. Additionally, the net debt, which is all the assets by the government minus the gross debt, is we succeed to maintain it negative, which means that the government will still hold significant assets, although they will shrink compared to the calibration year. The government used to hold almost the equivalent of that year's GDP in assets. We succeed to maintain it at 21% against 15% share of GDP as a debt. And more importantly, last but not least, it is the CO2 emissions which are abated by almost 55%. Looking at the employment, the sectoral composition of the unemployment, we see that the transformation scenario, since it is driven by labor-intensive sectors, we succeed to have more jobs creation under the transformation sector compared with the continuity scenario. We have around 270,000 additional jobs under this scenario compared to the other one. Of course, we have some jobs losses in the fossil fuel sectors, as we can see in the oil, in the gas, but those are largely offset by the manufacture job creation and the creation of jobs under the commercial and public services. Here is the outlook of the public budget balance. As you can see, the outlook is quite challenging for both scenarios, but it is more promising under the transformation scenario, since the budget balance can reach equilibrium as soon as 2024, recovering from a deep decline of 15% following the oil price collapse in 2015 and 2016. And this is largely built on the energy price reforms and the reform of the corporate tax, which means that looking at the debt outlook, we succeed to hold a net creditor position of the government at 21% of GDP in terms of assets, while it is expected to almost cancel or use all the buffers by 2027 under the continuity scenario. Again, it is very important to look at the CO2 emissions, since those are mentioned in the NDC scenarios of the kingdom. The gap between the two scenarios is around 500 million tons lower in terms of emission in the transformation scenario compared with the continuity scenario, which is almost 4 times the target that the government was set to reach by 2030, which is 130 million tons of CO2 emissions reduction.
Now you have 2 minutes left.
Yes, I'm at the conclusion already. So the main findings, just to sum up, this is a follow-up of the work that we did to assess the impacts of oil price structural decline in our previous work. We assess 2 polar scenarios that are mentioned in the national climate policy, the continuity and expanding energy intensive industries, or an overall structural shift of the economy toward low carbon activities. In our projections, 3 key takeaways. The first one is that we have higher activity, lower unemployment, lower debt, and lower CO2 emissions. So those are the 4 key points that are highlighted by this transformation scenario. Just to mention that since the conference last year was cancelled, we had a chance to submit and wait for the reviews and the paper, and you can find all those results and much more details in our forthcoming paper, which will appear shortly in the Energy Journal. Thank you for your attention. I just have to mention that the work was under CIRED affiliation, and I was also part of the French company EDF R&D, which was funding my research under the PhD convention that is mentioned here. And since then, I joined KAPSARC to continue working on these modeling aspects. Perfectly on time.
Yes,
Thanks,
perfect. Thank you very much for an interesting presentation. So again, we have time for questions, comments. Let me ask you meanwhile, maybe you said it, but in the electricity sector, is there a big switch in the transformation scenario from fossil fuels to like solar or other renewables?
Yes.
So we have a big potential for solar PV, I suppose, in Saudi Arabia.
Exactly, exactly. So all this information is captured by the bottom-up model, which has a very detailed representation of the electricity sector with many technologies that are represented. Of course, solar PV, solar CSP, nuclear, wind, and the gas with CCS. And what we do is that based on those scenarios, since we have a unique representation of the electricity sector in our transformation scenario, it is captured by an increase of the capital intensity of the electricity sector within IMACLIP. So we rely on the projections of the bottom-up expertise, and we adjust our electricity sector in our CGE model by increasing the capital intensity to capture the switch from fossil fuel to nuclear and wind and renewable-based electricity mix.
And I also wondered, so when you have a lower production, lower activity in the oil and gas sector, is that only because of reduced domestic demand, so that the export is the same, or?
Yes, so the production is the same. The production is the same, and it is based on the IAEA scenario. What is changing is the use of a fossil fuel internally, which means that under the transformation scenario, we have slightly higher exports of crude oil and refined products compared with the continuity scenario, since the switch in the electricity sector notably is not that dynamic under the continuity scenario, in which we will continue to have 100% fossil fuel-based electricity sector, including a lot of crude oil and refined products.
Okay. I don't see any other questions, so let me have a final one then. So you mentioned that oil exporting countries like Saudi Arabia and other OPEC countries, and also Norway, can see lower oil prices in a net zero scenario. So has there been any discussion or thoughts in Saudi Arabia of trying to get other countries part of OPEC, like a climate OPEC involving both Norway and other non-OPEC countries, to sort of cut back on oil supply to keep the oil price from falling too much?
Yes, so I think that there was an initiative of oil producers following the net zero initiative and the climate summit recently, which is led by Saudi Arabia, I think, and Norway is part of it. Canada is part of it, and I believe that Russia is part of it as well. But I think in the interest of everyone that the main focus of these countries now is to maintain stability of the market. Okay. Rather than get involved into such long-term scenarios, which will increase probably disrupt investment first, which is quite required even in such scenarios, and will induce a lot of volatility.
Okay, thank you.
Thanks.
Okay, thanks again for your interesting presentation. So I think we then move on to the third speaker, which is Gauthier de Maere. You have another last name that I leave it to you to pronounce. But the title of your presentation is The Role of Electrification in the Decarbonization of Central Western Europe. So please, the floor is yours.
Okay, thank Knut. So indeed, let me just maybe. Okay, can you see my my screen?
Yeah, now it's perfect.
Very good. Okay, excellent. Yeah, so this is work that I've been doing with colleague of mine of Engie. So I'm Gauthier. I'm working indeed for Engie Impact. So it's a subsidiary of Engie, which actually perform various consultancies services. And here we are in our team somehow. Energy experts helping here the strategy division of Engie. So it's work with Hugues and Pierre-Laurent, who are from the strategy team of Engie. And the goal here was to analyze somehow what's the role of electrification in the decarbonization of Central Western Europe, and just maybe to see what are we speak about Central Western Europe. So it's the country that are highlighted here just on the right, on the left of the slide. So so that's where we are going to focus my
so I don't hear you anymore. Is it only me, or
can you hear me?
Well, we can hear you.
Yes, we can hear you.
Okay, sorry, it's me.
Okay. So sorry. Yeah, if you have any issue like this, don't hesitate to raise. Okay. And so to try to see what's the role of electrification for those countries to reach net zero, because we know that carbon neutrality will require a mix of different measures. So energy efficiency, reducing demand, decarbonization of the different energies, of power, of gas, and so on. The electrification of end use, so switching the demand towards electricity, and then obviously doing deep reduction in agricultural emission and doing some sort of CCS or afforestation. And here I focus on the role of electrification, and basically one can have on the positive side of electrification. What is usually agreed is that the electricity sector is probably the less costly to decarbonize, thanks to the ever improving renewable technologies, and where also potential are the highest, certainly in Europe. And also using electricity directly somehow usually leads to fewer transformation loss. Okay, when you look at motors or maybe heat pumps to generate heat and so on, I mean, electricity have usually very good transformation efficiency in order to transform that energy into a useful energy. Then on the negative side of electrification is that, okay, switching the sectors to electricity usually requires investment in technologies that are more capital intensive. So if you think now about transport, EV, or even trucks running on electricity, or in the industry, changing all the different processes to electrification, and also heating. So heat pumps are more expensive than traditional boiler. Okay, and then the second negative part is actually that, okay, it can also lead to significant cost increase in the infrastructure. So in infrastructure, I mean either in terms of power plants that are available or in terms of network. And that would especially be the case if the consumption profile of the new end use somehow they coincide with a scarcity event. Okay, so somehow you see that the role of electrification has positive effect, has also negative effect, and we're not too sure about what should be then involved. And then the goal here was to develop some scenario to try to see, okay, what were the quantitatively assess somehow its importance and then its limit of that electrification. Okay, so during my presentation, in order to do that demonstration, I will focus then on three different scenarios. So a first scenario, which is called balanced transition, where basically here it's a scenario that is achieved by a mix of measures, where you have already a high electrification, so 55%, so of final energy demand that is served by electricity. And then also combined with large and diversified green gas development, and also a little bit of CCS, so with maximum 150 million tons of CO2 that can be stored each year for energy. Okay. Also, this scenario somehow wants to achieve an efficient implementation of sectoral coupling across all the sectors by benefiting from vehicle to grid, by relying on hybrid heat pumps, and also by integrating the electrolyzer on the sector. Okay. The second scenario, which is called massive electrification, so it's somehow here a decarbonization pathway, but where we try to push the electrification as its maximum, so really try to have the highest electrification than one can see. And here it reached 65%, so 65% of the energy in use are now met with electricity. So it also looks to have an efficient implementation of sectoral coupling, except that with the preference towards green electricity only. So you don't develop hybrid solution for space heating, and also the scenario disregards either CCS technology, and tries also to be as autarkic as possible. So with respect to the e-fuels, they're going to be produced locally. And then there's a third scenario, which actually is a slower decarbonization one, where basically Europe fails to reach carbon neutrality by 2050. And for the country scope, basically it's only reach minus 80% target. And also it lacks its political ambition stated in the Green Deal. So the national energy climate plan are lagged by 5 years. And somehow that scenario is based on the projection of current trends, and there's no drastic switch among the different energy vectors. Okay, so those are the different scenarios that I will use to quantify in order to somehow certainly more born by comparing the first two to see, okay, what are the impact of trying to have a very high or to push electrification as its maximum. As methodology, in order to compute that, so what we use is a energy system planning model. Okay, so here with a commercial tool called Plexus, and somehow we make a trajectory from now on up to 2050, where we need to reach carbon neutrality. We do that by a 5 years time step, but what is important actually is that we do that as early granularity, because our goal is really to assess, okay, what's the impact on the electricity sectors in its need with respect to flexibility. Okay, so what you have traditionally in energy system planning model, so assumption regarding technological costs, which is the capex, efficiency, operational maintenance cost, and so on. Then what constitutes somehow the storyline of the scenario? So what are the different final energy demand to be met? What is quite important here is that we made an effort to make sure that, okay, we could characterize that final energy demand also by looking at its associated hourly profile to take into account the seasonality and the thermosensitivity of the different energy end use, and also linked to that to ensure that we also have its flexibility potential to not exacerbate somehow or to overestimate what could be the challenges to be integrated on electricity. And so, for example, that concern a big potential is the potentiality to do vehicle to grid for the electrical vehicles. Okay, then we impose on that an emission trajectory as a constraint. And then, okay, so those are the three main energies we'll be looking at with a lot, obviously, of synergies between the two. As, for example, hydrogen can be produced either by electricity methane, okay, and we represent all those links with the different technologies that can be either on generation or on the flexibility side. And thanks to that, okay, one can have the traditional output of energy system planning in terms of capacity, in terms of projection mix at early level, in terms of CO2 emission reduction in the different sectors, and then also in terms of energy expenditure. Okay, so we use that model in order to quantify the different scenario. And yeah, I'll first start with detailing the demand outlook, okay, that we did with a bottom-up model, looking somehow at the storyline and how we translate that into the different energies and sector. So what you have here for the three energy vectors, so for power, for methane, and for hydrogen, it's used in 2020 currently in the geographical scope, so in Central Western Europe, and then detailed that by the different sectors of the economy. So first of all in industry, then in the buildings, and then in transport. And then a comparison then in 2050 for balanced transition, massive electrification, and slower decarbonization, how that demand evolve, and what are somehow the trends explaining the change. Okay, so maybe look at first at the power sector. So what we look is that, okay, in 2020 and compared to, 2050 compared to 2020, what we see is that, okay, in all the scenario, electricity improves and increase, while, okay, one sees that basically in the industrial sector or in the buildings, the increase in terms of terawatt hour is quite limited. Why is the case? Is because basically this increase is compensated by impressive energy efficiency measure. Okay, so both in the industry with switching the process to electricity, somehow indeed increase final energy demand, but then energy efficiency measure, also the additional efficiency linked to electricity, make that this increase is not as huge. The same in the building sector. So we are in scenario, for example, in massive electrification, where all the building stock is switched towards pure electricity heat pumps, and you see that the impact on the energy demand is quite limited, because on one side, all the large appliances in the different houses actually have a decrease in terms of their energy consumption, with also deep renovation of the building stock and the very good efficiency of the heat pump. Somehow you see that the impact on the total demand is quite limited. And then that leads to the main drivers of the future growth, which is actually transport, okay, coming from almost nothing, that gains exhibit a quite good growth in all the different sectors, but in all the different scenarios, obviously mostly for massive electrification, and then also with the ability to produce also e-fuel, so hydrogen and its derived product. Okay. Then when we look at methane, the story is quite the opposite. So we see that methane demand is shrinking for all the different scenario compared to 2050. a little bit in the industry, okay, where the most of the decrease is happening to massive electrification, because it's a scenario where we have the largest shift towards electricity for serving the different processes. Then also in the building sectors. What we see here is again in the transport sectors, and that's mainly in order to be able to decarbonize the good transport, the heavy trucks or the maritime sectors, switching to green LNG. Okay, then we have a little bit of gas to power in the different scenarios. So that's an output of the model. And also then the gas that can be used either to produce gray hydrogen or to produce blue hydrogen, meaning hydrogen that is produced with CCS. Okay, and then on hydrogen, okay, it's also a vector that is increasing in all the scenario, but one sees that okay, in massive electrification, that's where the growth is the highest, because one needs to produce all the e-fuels locally, and so that corresponds to also that big increase here in the power demand. Okay, so those are the different energy demands, so that we launch into an energy system planning model. And now I will present you the different results that we found for those three scenarios. So I'll start with the power generation. Okay, so we start here again for power generation in 2020. And so what I like to focus on is actually the share of variable renewable, and then the share of the gas turbine unit in the generation, and then how it moves with respect to the three different scenarios. And so one sees that actually variable renewable constitute the vast majority of the electricity production in all the different scenarios. And then actually what changes is what's then the energy supply by the gas thermal plant here in terms of total energy. So which is actually quite limited in massive electrification, so only 2%. And then it's 11% here in the balance transition. And it's mainly because here you have here the possibility to do CCS, and so thanks to CCS you lower the cost, the variable cost of those gas units that then automatically then produce for larger amount of the total energy. Okay, and then in the slower decarbonization case, okay, we still have 7% also of the production thanks to the CCGT, so the gas thermal units, and that's because okay, we don't achieve a full decarbonization over there. Still, that scenario is also relies on an almost complete power sector decarbonization. Also, what is interesting is to see that I mean we are here with early results, and so what we like to see is okay, what's somehow the flexibility needs in order to manage the different variability of the renewable, and somehow that is achieved by different means, by having flexible demands. So first of all, the electrolyzer that are there to absorb the excess production of renewable power, also that can actually accommodate for the seasonal fluctuation of, for example, of the PV panels. And then the electrical vehicles, thanks to their battery, by doing vehicle to grid, that can also accommodate for the more short-term fluctuation of the intermittencies of renewables. Then on top of that, the model decided to build additional batteries, and also in order to ensure that the system is not under stress in the winter when there is low wind input. The model also builds some gas assets in order to have firm capacity. Okay. I'll maybe jump now to actually look more about what is a big difference between the two decarbonization scenario is the benefit of having hybrid heat pumps in order to reduce the winter power peak. Okay, so hybrid heat pump are basically in pump complemented by a gas boiler. Okay, and why is that? Is because heat pump suffers from two main two main drawbacks. The first one is that when actually the temperature starts to be cold, the efficiency of the heat pumps also deteriorates. And also actually that goes in also in the fact that it's not very efficient to oversize the capacity of heat pumps, because it also leads to losses in efficiency. Okay, so that's a first one. And so heat pumps are always somehow
2 minutes left
combined with. Okay, so I'll jump then I'll quickly comment on that and then go to transition cost. So what we see here is basically the operation of the heat pump, then switching to gas here during the stress period that actually allows here to reduce the peak demand. I'll switch. I'll not present actually the different outlooks that we have on gas demand and so on, and then I'll focus rather on the scenario cost to see somehow where we saw the main difference between the scenario. Okay, so here that's the scenario cost of my three scenario expressed in billion euro per year, so levelized cost. And indeed what we see is that having a massive electrification actually leads to an increase of transition cost in the different sectors. So in transport, that's where it's noticeable, but also in buildings and in the industry, and that increase actually represents 30% of the transition cost. So we did several sensitivities to see if that result was more or less robust. And so we did that by varying either the capex and by making all the electricity technologies more expensive, or making all the technology producing green gas more expensive. And what we saw is that basically the difference between the two scenarios didn't didn't change drastically, with a balanced transition being less expensive than a massive electrification. Second one, where we also look at trying to see where does that come, that robustness. So we did basically several sensitivity by removing one of the flexibility option or potentially or coupling option between the different sectors, and then looked a little bit, what were the increase of cost, or what were the savings that coupling the different sectors were allowing to do. Okay, and for the sake of time and leaving you the opportunity to ask question, I'll then just somehow conclude, just to show that indeed somehow it's important to have basically a mixed panel of the 5 different options to decarbonize, and that only relying on energy efficiency and electrification actually put the energy transition in danger, because it leads to additional cost. Also, what we see is that basically in terms of development pace of new wind and new solar is actually looks very difficult to reach. And then also with respect to the power peak demand, that also is very much increased, and that will somehow exacerbate power adequacy problem in the power system. Okay, so thank you very much for attending this presentation, and I will take your question with pleasure.
Thank you for a very interesting presentation. Questions? Raise your hand. Yeah, Salaheddine.
Thank you very much, Knut. Thanks, Gauthier, for the presentation. One quick question. Do you have any assessment of the impact of your scenarios on the final price for the consumer for each scenario? For example, electricity prices for households or electricity prices for the industry. Is it an endogenous output of the model or not? Thanks.
Yes. Yeah, thank you, Salaheddine. So indeed, it's an output of the model, and so that's how we compute the scenario cost. Somehow you see that the first block of the scenario cost are the energy expenditure, so meaning the price times the different demand, and that is actually the case for the different energies, and so for power, for gas, for hydrogen, and so on. And indeed, so we didn't show it in terms of cost per consumer, because I mean, some of the costs are not necessarily direct linked to household, and so that's why we prefer to show the numbers in terms of total value, but that's something that would be doable. Yeah, maybe something that also is interesting is that with respect to the power costs, what we see is that it really depends on the end use. Somehow, if you have an end use that is very flexible, like let's say the charging of your EV battery, so the cost is way lower compared to, for example, the cost for space heating, because there you ask power when during the time where it's the most difficult to supply it for the power system.
Thanks. And is it doable to have the decomposition of the unit of energy by the breakdown of let's say 1 kilowatt hour of electricity by the cost of supply, cost of transmission, and any hypothetical taxes, or not?
So you want to have you're asking about the breakdown of the electricity cost
of the final on the impact on the final prices for the end user. The price that is paid, they say, by households or industrial users or whatever.
No, indeed. And so here, yeah, for the sake of the presentation, I didn't show that, but indeed, so what we've been analyzing also is somehow to have a breakdown of the cost in the different bricks, and somehow to also show, okay, what's the impact somehow about yeah, the need to reinforce the network. For example, if the peak on the DSO side increases, also to integrate renewables, the cost necessary to reinforce the network, and so on. So we do have that breakdown. So everything actually is compacted here. What you can maybe see here is actually the difference between what we call somehow the infrastructure cost, so everything related to network or to the different equipment, and then what's the cost with respect to the energy expenditure. And what we see, I mean, what is quite intriguing is that, okay, the energy transition somehow, the infrastructure costs are somehow more prominent compared to the energy expenditure. And this is because somehow the energy is actually, while the price are actually rising, their demand is also failing, and so that somehow mitigate the increase of cost in energy expenditure.
One quick, just to make sure something. Another question, if you may allow me.
Very quick.
Yes, just very quickly, Gauthier. What is the granularity of the representation of the model? For example, let's say in France, how many nodes do you have represented, and does the model allow for interconnections, expansions, new builds?
Okay, so it's a zonal model at country level. Okay, that works at all level, and yeah, interconnection plan are taken with the most optimistic case of NSUE. So we don't endogenize that choice. We cross-checked after, and somehow there is no not case for yes for optimal investment after when looking at the results. Somehow with the flexibility that is quite cheap, there's not a huge economic case for reinforcing the line.
Okay, thank you very much again. So
thanks.
Yeah, so then we need to move on to the last speaker, Sneha Thube. So if you stop sharing with here, and then
yes, let me just do that. Stop share. Excellent.
Good. So then you can share. And the title of your presentation is then "Why the Wide Range of Cost Estimates for Fulfilling the NDC Pledges, a Meta-Analysis."
You're seeing the full screen, right?
Yes, perfect. So
Great.
please go ahead.
Thank you. So thank you for being here, everyone. I'm Sneha Thube. I'm a junior researcher and a PhD candidate at the Kiel Institute for the World Economy. And the paper that I'm presenting today, it's work in progress. So any comments, criticism are welcome because we will be able to incorporate them. And it focuses on sort of understanding why, because the previous speakers, everybody has presented a modeling study, and similarly, there's several such studies out there in the literature. And what we're trying to understand in this study is, why do we have such wide range of cost estimates when it comes to fulfilling certain climate targets? And we use a meta-analytic approach to work with this. So to sort of go to the motivation and kind of set up the stage of how we arrived at this study, in 2019, so spring 2019, there was an inter-model comparison study that was jointly organized by the Kiel Institute and the University of Oldenburg. And it was also in cooperation with the Energy Modeling Forum, which is this structured forum which supports and organizes studies that are typically focused on a specific topic each time. So this was the EMF 36 study, which focused on the theme of carbon pricing after Paris. And the way it works is that the organizers invite CGE modeling teams to participate in this. So invitations were sent out, and then teams which have resources to participate, they usually accept this. And then what is done is that you have this introductory meeting where teams meet together, they kind of figure out the topic, what kind of scenarios they want to work through, understand the modeling needs of one another. And then in the end, hopefully what happens is that you arrive at a common set of scenarios which every team will model. And having this common set of policy scenarios allows you to compare the results between studies and sort of get deeper into what kind of range do we get for a particular policy scenario from different studies, and what are the main drivers behind it. So in our study, there were 17 teams which participated, 15 out of which had global CGE models and 2 had national CGE models. Out of these 15 teams, we had 15 models, 6 were static, 9 were recursive dynamic. So there's definitely a lot of variation in the kind of model that each team brings. And each of this model was focused on the GTAB9 database with the base year of 2011. And this is kind of like a figure which sort of condenses the scenarios that were modeled in this study. So we had these 15, I hope you can see my pointer. Yeah. So we have these 15 models that participated. And then, as we said, that each team has to model a common set of scenarios. So in this particular EMF study, the baselines themselves were also harmonized across models. So we picked 2 baseline scenarios coming from 2 data sources. So the IEO baseline comes from the US Energy Agency forecast, and the WEO comes from the International Energy Agency's forecast. And each model calibrated their baseline to these 2 specific baseline projections until 2030. And then commonly, 3 climate targets were also agreed, which are, of course, based on the most recent climate agreement that we have in place, which is the Paris Agreement. So the NDC target represents the unconditional pledges that were made by countries. The NDC plus target is a representation of the conditional NDC. So it's stricter for some regions than the NDC target by itself. And then the NDC 2-degree target was basically a scaled up what if kind of policy scenario where the NDC targets were scaled up and calculated such that globally the world is on the 2-degree pathway. So as you go down, the stringency of the targets increases, basically. And then in addition to these climate targets, there were 5 cooperation scenarios, as we call it, that were implemented. So let's just, maybe we don't focus a lot on the details here, but basically the REF scenario is a scenario where none of the regions in the models cooperate with one another. So it's a unilateral regime. And on the other extreme, you have a global scenario where all the regions cooperate with all of their sectors in a global ETS. So they are very representative scenarios, let's just say. I mean, the global, I don't even think that's very likely in the near future. So it's just kind of representing two extremes of how cooperation could look like. And then in between, we have these three scenarios of partial cooperation. So Asia is a scenario where Japan, China, and South Korea have an ETS amongst themselves, and the rest of the world has unilateral action. China is like a coalition between Europe and China, and partial is a coalition between the energy intensive sectors across all of the regions. So it's a sectoral ETS and not specifically between certain regions. So this is kind of the setup of the entire study, and unsurprisingly, we had a lot of data, a lot of results coming from it, and this figure kind of summarizes the CO2 prices that were coming out of this study. So I know it's a lot to take in, but let's just focus on the essentials. So each of these bars with different colors represents one of the policy targets, so either the NDC, NDC plus, or NDC 2-degree target. And then the darker and the lighter shades represent the two extreme cooperation scenarios that we talked about. So the darker shade is full cooperation. So we usually have lower prices when there's complete cooperation. So that's what it represents. And the lighter is this unilateral action, so the REF scenario. And along the horizontal axis, you would, of course, see the different models that participated and the outputs that we got from these models. And there's a lot of variation in the results. So if you look at just the NDC, so the blue bars, the NDC targets, the prices of reaching the mitigation level with a global ETS could vary from somewhere around $10 to $12 per ton of CO2 to something like about, I would say this is 70 or something. And then similarly, even for the other policy scenarios, so for the green bar, so the most strict target that we have, the 2-degree, the prices again vary from somewhere around 25 to, more than 150, I would say 160 or 162 or something that this price is. So, I mean, this is what we expect, and this is why we have these intermodal comparisons, because we do want to see what the ranges are. But kind of what we were wondering is that, hey, we had the same baseline, we had the same targets, we had the same cooperation scenarios, and despite that, there's a lot of variation. So can we go a bit deeper into why this is happening? So, yeah, this is again the same kind of representation of results, but with welfare, that again, yes, we have a lot of variation in the welfare effects. So what happened is that the study was more of an afterthought, I have to admit. So when we looked at all of this variation in results, we started examining a bit more how the models varied structurally and parametrically. So definitely there were differences between the structural assumptions behind models. And then the strength of this kind of intermodal comparisons is that you can definitely identify certain outputs where all models agree, and you can make a definitive statement about it. But of course, there's also some contradiction, some variation, or some ranges that are coming from these different results. And we wanted to focus on that particular aspect. So trying to really discern what are the key factors behind these differences in the range of results across the studies. So we went a bit into the literature of how people have done this before, and we came across this meta-analytic approach, which we really liked, and kind of it fit with the data that we have and the question that we have at hand. So meta-analysis, it's a body of statistical methods, which is very, very useful, and it's often used to review data from different empirical studies, and it's quite often used in the medical sciences, and you of course see that in economics as well. And what is usually done is that you put together results from different independent studies, and you create this meta data set. And then using this, you can perform like a regression analysis. And what you get, the idea is that you get more insightful and kind of layered results from it, which maybe you cannot derive from a single study. So as modelers, I mean, we know. So if we want to do like a robustness check for our study, we do something like a sensitivity analysis. So you pick up different, parameters from the model, which you think your results are sensitive to, and you kind of vary them in a range and show that, okay, this is how our results look like, and this is the range at hand. But this is a little bit of a different approach where you put together different models by themselves. So you can also really get into the structural differences that different models have. So in our study, we follow this meta-regression analysis approach. And what we do is we pick one summary statistic variable from each of these models, which is our CO2 price in 2030. And the independent variables, they include different features of the model. So some of these features are structural parameters, so something that would be a modeler's choice, and it's determined well in advance. So it's not coming from the policy variables per se. So things like what kind of trade structure you want to have in your model, whether you want a static or a dynamic model, would you allow factors to be mobile across sectors, regions, this kind of stuff. So it's really decided well in advance. So it's quite, I mean, that is, I would say, independent decisions, and they're not influenced by the study that you're doing. And then we also have a set of policy variables that we look at. And like I said, in specifically related to modeling studies, there have been previous articles which have looked into this. And just to name a few, it's Repetto and Austin from 97. Then there was another one in 2006, which was also based on another EMF study. And then we have from 2009, a study on, I think it's non-CO2 gases. So what we did was that we defined these these variables based on the models that we used in this EMF 36 study. And that was, of course, the database for this entire exercise. And the model variables that we focused on were the regions, the number of regions that each model had, energy variable, which is a total number of energy sectors that each model has. So in the GTAP database, the primary sectors, energy sectors, they are disaggregated within the database, but the electricity sector, depending on whether you use the main GTAP database or you use an add-on data set that called GTAP Power, you could have either one sector for electricity, or you can differentiate between the different electricity technologies. And some models even do this independent of the GTAP Power database. So just they have their own method of disaggregating electricity in their model. So we had an indicator for how many sectors you have in your model. Then unemployment. So typically, at least the studies that we have, the models that we have, they do not characterize unemployment within their structure. And it was just one model which did this. So we had an indicator for it, but we're still a bit unsure. I mean, it's just one model in the end. Then static versus dynamic. So dyne is again a dummy, which is 1 if the model is dynamic. So 9 of our models were dynamic and 6 were static. So we differentiate between this. Then certain models, they allow for endogenous technological change. Not all of them, but so we wanted to capture this because, I mean, basically all of these variables, there is a theoretical backing behind why these are considered important or to some extent determiners of the cost. So they get, I mean, in the full paper, we do refer to literature which supports this choice of variables. So of course, there's plenty of literature on why endogenous technological change makes an impact in the modeling results. So we had an indicator for that. And then we had this ALE type indicator, which is again specifically focused on the electricity sector. So again, not all the models differentiated between these different kinds of electricity technologies. So quite a few models, they just had one electricity sector. So you cannot really say how the composition would look like in this sector. But there were other models which differentiated between solar, wind, hydro, nuclear, and then sometimes even bioenergy, and then they had the conventional fossil electricity sector. So we just have one indicator to capture this. So either you differentiate between them or you don't. We don't go more into details about this. And obviously this ALE type variable, it's correlated with energy, so we don't use them at the same time, because if you differentiate between electricity types, you would have higher number of total energy sectors. And then lastly, we wanted to use an element like a variable which was indicative of the trade structure in the model. All of the models, actually, they use Armington trade structures, so we couldn't have a differentiation at that level. So we started with something that we could condense to a single value and would still capture the differences between models. And for the moment, it is an indicator about the source of the G-type of the Armington elasticity. So we noticed that not all of the models, even though they're based on the G-type database, not all of them use the G-type Armington elasticities. And quite a few of them, they have other sources, or they either cap their Armington elasticities at certain values. So they kind of have like a hybrid approach, I would say. It's not necessary that they use completely different, but there's some gray area in there. So we set this Armington variable to be 1 if a model strictly uses G-type elasticity, Armington elasticities for all of the sectors, and it was 0 otherwise. And then moving on to the policy variables, again, very naturally, they're based on the climate targets that we put in place and the coalition definitions that we had in there. And these two variables were defined as categorical variables. So the results that you see would be in reference to the reference scenario for the results. So for the CLIM target, the coefficients for NDC plus and NDC 2 degree target are relative to the base case, which is the NDC scenario. And for cooperation, you have different levels of cooperation relative to no cooperation at all. And the left-hand side variable, so the dependent variable, was a log of the CO2 price in 2030. And we performed a simple OLS regression with this. And yeah, I guess we remember, I'm just assuming that we remember this different scenario structure. So I know, I mean, this is basically the results. I know there's a lot to take in, but let's go through it a little bit bits and pieces. So if we just focus on the first column, which shows the results for the global CO2 prices, and what we sort of see is that the variable regions is it has a positive coefficient and it's significant. So because regions was also used as a logarithmic variable, so what you see here is an elasticity. So it has a positive elasticity for the global CO2 price. Similarly, well, not similarly, but then when you move on to the rest of the variables, you have dummies in there. So again, the signs show you, yes, whether the CO2 price increases or decreases with this variable, but you cannot interpret the size, the effect size immediately, but you would have to convert it. So unemployment, for example, in our study, from this database, it shows that models which have unemployment characterized within themselves in the model structure, they have the CO2 price lower by 42%. So that's something. But again, as I said, this was only one model which did this, so we're not emphasizing too much on this right now. Then models.
You have 2 minutes left now.
Yeah, thank you. Similarly, then models which have endogenous technological change have lower CO2 prices. And we think that's because there's a scope for adjustment within the model. So as the climate policy is implemented. Then we see that like having a detailed representation of the electricity sector, having a dynamic model versus a static model, both of these are associated with higher costs, and our like very intuitive understanding is that it basically captures the friction sort of in adjustment, so therefore there are higher costs, and it's a more realistic representation of the world. Similarly, we see that models with GTAP elasticities, they usually have higher CO2 prices. Now, in the policy side, again, the results are not surprising. It's sort of what we expect. So the CO2 prices are increase as the stringency of the targets increases, which is what we expect. But the interesting part is the coalition. So, I mean, yes, we expect that in CGE models, when you have cooperation, the CO2 price has to go down because that's the gains from cooperation in that introducing the CO2 price. But when you look at it globally, only the coalition Asia and the global coalition give statistically significant reductions in CO2 prices. So, and while the others, they do not. And then just like one quick glance maybe at the regional level results. So what we also can look at from this table, so now if we focus on these two columns, which are results for China and Europe, when they are part of the Europe-China coalition, again, let's just skip the model variables, but in the policy variables, like there are these interesting patterns that we can see that the CO2 price for China increases. So it's positive, while the coefficient is negative for Europe, so it decreases. So this is the adjustment. When these two regions are part of the coalition, the CO2 price for China increases relative to its unilateral action, while it decreases for Europe relative to its unilateral action. And these are the sort of results that we're able to get from this table. Yeah, I think I'm running out of time, so I'm not going to go more into the details. But basically, what we can get from this table is not just the effect on global CO2 prices, but also regional CO2 prices for different coalitions, different policy targets. And I think this is a very layered table, and we ourselves are kind of going through it and trying to put it in a way that it's understandable for in a paper format. So, yeah. Sort of concluding, so what we thought this was quite interesting because CGE models are by themselves deterministic in that sense, so they don't surprise you a lot sometimes. So having this sort of meta-analysis, it tries to put results more, and condense the results from different models and try to understand why the results from different models differ, even though they have the same policies implemented in there. So we know there are two big chunks of variables, structural and policy variables, which drive this. And with this study, we're trying to get a bit deeper into which structural variables and to what extent policy variables and how they affect the results. Yeah. So thank you for your attention.
Thank you very much for a very interesting presentation. Questions? Let me ask you one.
Yeah.
So you mentioned the Armington elasticities, for instance, that you had two different. So we had a dummy, either this group or this group, or this source or this source. So did you consider to look at the level of the Armington elasticity, like the average level, and also for other elasticities? I mean, substitution elasticities in the production tree between capital and energy, for instance, or between different energy goods. I suppose that's quite important for the CO2 price.
That's true. So we did start, yeah, so when we were constructing this Armington variable, we did consider doing like an average across sectors. But, well, we're not that convinced if it provides a lot of information. I mean, it's an average in the end, and the variation is quite a bit across different sectors, even within the GTAP database itself. So we were not quite sure if it really provides us a good, a good variable which we can use to make some sort of comparison. So we didn't do that yet, but maybe it's something worth a try. Actually, we haven't tried that. And when it comes to the other elasticities, so between capital labor or capital labor electricity, the kind of challenge is that the models have very different production sectors. So sometimes at the base, they have capital and labor as one aggregate, and then they aggregate it with electricity. So, but then there's also differences in how this is done. And we were not able to kind of quantify all of these differences in one variable. So I think the big challenge we're having, so the great thing is that we have access to all these models and the teams, and they're more than happy to cooperate. But the problem is that it's difficult to identify variables which you would be able to quantify in a single number, and they're still meaningful. So this is where we kind of went back to the previous meta-analysis studies and the literature and sort of put these two together to come up with something that looks very simplistic, I admit, but that's what we can quantify.
Yeah, I think it's very good that you try. So we have one more question or comment, please, Masa.
Yeah, so Sneha, thank you very much. I was running the EMF 35, which focused on Japan. So it was really great to see what you have, accomplished. But my question is, so I was really surprised to see a very high R squared number, and like it was like 0.8. But I started wondering if what would happen if you exclude the policy stringency variable, because obviously if you go from NDC plus to NDC plus to the 2-degree target, then you enormously increase the carbon price across models. So but I feel like policymakers are more and scholars are more interested in the variation of a carbon price across for a specific policy target. Why this model behaves in a particular way. So do you have any thought on that?
Yeah, so we do have that table in the full paper.
Okay.
So of course you're right, like because we put together all the different policy scenarios, our results are driven by the policy variables, but we did separate tables for just the model structural variables for each policy, each target. So each coalition, each target. And there, of course, the R squared is much lower. I have to go back and check, but it's between 0.3 and 0.5. So
but
it's
still 0.5. That's good.
Yeah, for some, not for all.
Okay.
For some.
Okay.
Yeah. So it's somewhere between this range, and of course, there's yes, we cannot explain all of this variation just with these small 5, 6 structural variables, but yeah, we do have that table in the full paper.
Okay.
Thank you very much. So it's now 5 past or 6 past 11, so I think we have to close this session. So I want to thank everyone, especially your presenters, for a very interesting session, very interesting presentations. And I wish you a good rest of the conference and also a nice day. So thank you, everyone.
Thank you.
Thank you, everyone. Bye-bye.
Thank you.